So I want to show you what we're talking about when we're talking about the stereospecificity of an E2 reaction. What's going to happen here is this is the proton, and it's going to get plucked off by a base. That leaves these electrons here, which will go to form a double bond, and then the bromine will leave at the bottom. Now for this, and that leaves us with this structure with the double bond. For this to occur, these have to be in the same plane. So the hydrogen here, the proton, these two carbons, and this halogen have to be in the same plane. And you can see, if you look at it as like a Hoffman projection, that they're all in a staggered conformation. If they are in a conformation like this, then we get a eclipsed form, and that's not stable. That's not going to happen. So for an E2 reaction, we have to have this conformation. For an E2 reaction to occur, the hydrogen, the carbons that are going to have the double bond, and the halogen must all lie in the same plane. And they must be anticoplanar to each other. So one has to be down and the other has to be up. We can see this when we look at the projection, the Newman projections, that the bromine needs to be up and the hydrogen needs to be down for this reaction to occur. If they are syn-coplanar, so that they're both up, if we look at the Hoffman projection, we can see that they will be eclipsed, and that's not going to be a favorable reaction. So the product here will depend on the starting alkyl halide. If we have the R groups, the red groups are both up, and the blue groups are both in the down position, the red groups will be on the same side of the double bond, and the blue groups will be on the same side of the double bond. If the one red group is up and one red group is down, and one blue group is back and one blue group is up, we end up with this configuration of red, blue, blue, red. This only happens when there's only one hydrogen to take off. So there's only one configuration. That's the only way that we can get a stereoselective process. Otherwise, if there's more than one beta proton available, then you'll get two stereoisomers. So now let's see what happens if we perform an E2 reaction on these two molecules. If we look at them closely, we'll see that this first carbon, they are mirror images. But the second carbon, they are identical. So these are diastereomers. We need to get them in the right position for the elimination reaction, so we'll twist that single bond. A base comes along and steals this proton. Now we have a double bond between the two carbons, and we lose the halogen. This molecule, we end up with a red one and a blue one on the top, and a red one and a blue one on the bottom. With our other molecule, our diastereomer, we put it in the correct position. We pluck off the proton, it's gone. These electrons are now making a double bond here between the two carbons, and we lose the halogen. But look, with this molecule, we have two reds on the top and two blues on the bottom. So we've made different compounds, and we're being stereo specific With this particular molecule, there's only one proton that can be removed, and so we make a very specific product. So let's look and identify the major and minor products for these reactions. Okay, so here's a double bond. Here's our carbon, alpha carbon. If we go this direction, there are no hydrogens, so there will be no double bond formed here. On this side, we have a hydrogen that's on a wedge and one on a dash. So we've got two hydrogens that we can pull from. And so we'll get two stereoisomers. We'll get our ring. A double bond here. And then our bulky group on the end. We'll also get this is the trans. We'll also get the cis version. Depending on the orientation when the reaction occurs. So in this compound, here's our alpha carbon. This beta carbon has no hydrogen, so we can't go that direction. And this one only has one hydrogen. So we only have one hydrogen that can be made to do this reaction, and we'll end up with a trans. So if we treat compound C with a strong base, this is our alpha carbon, this is a beta carbon, but there are no hydrogens here, so there will be no double bond formed between these two atoms. Here we have just one hydrogen, so this reaction will be stereospecific, not stereoselective. We'll only make one compound. The way these are arranged, this is on the halogen is on a wedge, on a dash, and the hydrogen, or the proton, is on a wedge. So they're already arranged in the antiperiplanar planar relationship that they need to be in. So we'll redraw the compound. And this will be our structure. Redraw it with a double bond, take off the bromine and the hydrogen. Make sure that you make this methyl group planar, because this is a planar molecule. Okay, what about here? We've got the alpha carbon here. There are no beta carbons, no beta hydrogens here, so we can't have a double bond this direction. There is one hydrogen here. Okay, so we've got one on a dash. Dash. So the halogen is on a dash, and we have one on a wedge. So we are in the correct configuration for elimination to occur. So we can just redraw our structure. Really bad. And that will be our structure. I want to do one more, and I'm going to have to give myself some space. This is G in your book. It's got halogen right here. Okay, so this is very similar to this one. It's minus this methyl group. So we've got 2 hydrogens that could come from here. And because of that, we will get 2 products. We'll get a product that looks like that, which is the trans, which is the major, and we'll get this product, which is the cis, and it's the minor. So this is a stereoselective, not a stereospecific reaction. Now we can also have... Now let's look what happens with a ring and an E2 reaction. This is our halide, and it's going to, these are our 2 protons, one of which is going to be removed by a base. Now we'll need to be in a paraplanar position for this to happen. And as you can see right now, with the halogen at an axial position, we are not paraplanar with either of these hydrogens, so our protons. So let's switch it so that we do a flip. And I can look you right down the barrel here. So now this halogen, this carbon that's behind, and this proton are all in the same plane, so our reaction can occur. So for an E2 reaction, the halogen and the proton that's going to be involved in the reaction have to be in the axial position. So stereospecificity in E2 reactions on substituted cyclohexane. What you need to know about this is that the E2 reaction can only occur when this is the format, when the chlorine and the hydrogen are in this antiparaplanar position. That results from them both being in an axial position. One will be up and one will be down. They need to be next to each other and they need to be axial, and that will give you the proper configuration for an E2 reaction. So in order to be antiparaplanar, the leaving group and proton must be axial. An E2 reaction will only occur if they're both axial, and that results from one being on a dash and one being on a wedge. So let's see how that works. If we've got our wedge and dash diagram here, and we'll put our chloride, it's our halogen, on a wedge, and I'm going to put a methyl group over here and another methyl group over here. So this position is blocked. There are no hydrogens over here. On this position, we're going to have a hydrogen, a proton on a dash, and I'll put a methyl group on a wedge. So let's translate that and put it on our chair. I'm going to, because I know I want this to be in a axial position, I'm going to put this chlorine in an axial position. I have to put it up because it's on a wedge. And each position has an axial and an equatorial one of them will be up and the other one will be down, and they will alternate as they go around the ring. So this is axial and up. The next position here will have an axial that goes down and an equatorial that goes up. Now our up equatorial has got that CH3 on it, and this has our proton. On the carbon on the other side, this is axial and up, so this one must be axial and down, and the equatorial will be up. Okay, so these atoms are now in line. They're planar, antiparaplanar, and they're in the correct position for an E2 reaction. Now, if I have a wedge and dash, and I've put my chlorine up, this time I'm going to put the hydrogen, the methyl group on a dash, and this on a wedge. This is my hydrogen, and we'll just block this with CH3, CH3, just to block it so we can't go that direction. If we translate this to this diagram, the chloride is still up. We need to put the hydrogen on the, so we've done this carbon. Let's do this carbon right here. The hydrogen needs to be up. Well, on this position, that's an equatorial position, and our methyl group ends up in the axial position. So we're not in the proper position to have a reaction. And so this will not undergo an E2 reaction because there is no hydrogen in the appropriate place. Okay, so neomethyl chloride is 200 times more reactive. It's got this group that's going to kind of want to hold, this is going to want to be in an equatorial position, and it's in the up position. So here is an equatorial, and it's up. Let's number these. So the second carbon has a chloride that's up. So this has an equatorial that's up, its axial was down. So the axial will be up here. That's good news. All right, we'll skip 3. 3 has, well, I'm going to go ahead and draw 3. I'm going to go ahead and draw, because we've got hydrogens that I'm interested in seeing where they are. There's a hydrogen here that's axial and down. There's a hydrogen here that's axial and down. And there's actually one also that's equatorial and up. And then we've got this methyl group, and it's on a wedge, so it's down. So it's a methyl group down here. And I haven't drawn in all the hydrogens, just the ones I'm interested in. So this can react with this halogen, can react with this one on the right, or this one. Let's see what happens with this compound. This needs to be up, and it will prefer to be equatorial because it's kind of a bulky group. Here we have the chloride, and it is in the down position. It's 1, 2, 3, 4. So it will be in the down position. The up here is axial, so the down is going to be equatorial. And we'll have, skip this, this is the same. So this group here holds the chloride in an equatorial position. And so this is much less reactive. chlorine is equatorial, or preferentially equatorial. Okay. We look at this, we find that only one elimination product is observed with these two compounds. And so let's look and see. For the neomethyl, you can have a double bond between this one and this one, or we could have a double bond between this one and this one. So we could go either way. We could take either this proton or that proton. For this one, if we draw it in our in a position so that it's equatorial, we have a proton here that can be taken off, that's on a wedge, right? But the wedge position here is taken up by this bulky group. So there's only one proton that's available, that's even available for a reaction.
So let's look at this E2 reaction. We've got a ring, and we've got our halogen here, and we've got a couple of protons. So let's look at them. This halogen has to be in an axial position for us to have our reaction. And the proton that it's involved with also has to be axial. So we've got this, it's in the same plane with this carbon and this carbon, but our proton is not in the same plane. It's off to the side in an equatorial position. Instead, we have this blocking group. So this reaction will not occur. It will not form a double bond here. Let's see what happens on the other side, though. On the other side, we have the halogen going straight up, and we have a proton that's going straight down. Straight up, straight down. They're both in the axial position, and we can get these three atoms in the same plane, and so the reaction will occur on between these two carbons. So we'll get a very selective elimination with this particular ring.
So in problem 24 here, we're asked to predict which of the two following compounds will undergo an E2 reaction more rapidly. To do this, we'll need to draw the chair forms from the wedge and dash. So it looks like we've got plenty of protons. Okay, so this is in the up position. So first I'm going to draw it in axial. I have to choose to draw it either axial or equatorial. I chose equatorial. This is 1, 2, 3. So this is 1, 2. This is a third position. It's going to be up. Axial goes up, down, up. So the chloride will be here. This is not going to be a very favorable conformation. This large bulky group would like to be equatorial, not axial. So let's draw it axial. It'll still need to be up, so we'll choose this position here. We'll make it axial, and we'll make it up. And that'll make it very happy to be in that position. And then let's look, the third carbon needs to have a chloride that's also up. So the way the things work, they alternate. So this is axial and up. This one will be axial and down, and this one will be axial and up. So the up position at this carbon is going to be at equatorial. Did I say axial? I think I did. Okay. And this is the more favored position. However, this puts that chloride in an equatorial position where it can't react.
So let's look at this one. I'm going to start the same way I did the other one. We'll start by making the T-butyl group there and we'll make it axial. We'll skip one. This one needs to be down. Well, what are things doing at this position? What are the positions? This one's axial and up. This one is axial and down. This one is axial and up. So this one will be equatorial and down. So equatorial and down from here, equatorial and up here, equatorial and down here. And but this is not a very favored position. Because we have this really large group in an axial position. It would rather be equatorial. So let's draw an equatorial here. This is the more favored position. And so we need to skip this one. This one needs to be down. And at this position, that will be an axial position. And that puts this chloride in the correct position for an E2 reaction. And this is also a favored position. And so this one will react more quickly. So let's draw the products. When we draw the products of these reactions, we're going to need to consider regenochemistry, i.e., will the reaction go this way? Will we take a proton from here and get a double bond on this side, or will we get a double bond on this side? We also need to consider stereochemistry. Make sure that we get whether it's going to be an E or an S, and how many different possibilities there are. So if we look at this, this is our alpha, and we've got two betas. Each one has a hydrogen that we can take. This hydrogen is on a wedge. So we have both of these compounds on a wedge. We'll need to do some rotation, and we'll get will be our final product. Sorry, we'll have to have some, we don't lose those double bonds. And we've made a double bond between this one and this one. Well, let's change colors, and we'll also can make a double bond, but we can take the hydrogen off this terminal one. And for this we'll get So for this reaction, we've got our bromine on a wedge here, and we have a hydrogen that's on a dash on this direction. We also have a hydrogen that's on a dash over here, and I should have done that at a different color so we could. The hydrogen here that's on a wedge is not available to react. So let's go back to our orange, and these are our two products. Got a methyl group, make sure I put it in the right spot. And we also can make, we take this hydrogen, we'll make this product. All right, so which one of these is going to be the major? Which one is going to be the minor? Well, this one is more substituted. It's got 3 substitutions, and this only has 2. So this will be the major. And this one will be the minor. If we look at this, we have the same reaction. This is the same substrate. We have a different reactant here, and so we'll get the same products that we got before, but what will happen is they will be in differing amounts. This one will be the major, and this one will be the minor. That's because this is a big, bulky base. Big, bulky base.